Hello and welcome to another video. In this video we're going to be continuing on with the TypeScript line 75 and we're going to be doing meeting rooms 2. So here you're given an array of meeting time intervals where, same thing, intervals start end, return the minimum number of rooms required. So the difference between this question and the first one, which makes this one a significant amount harder, is you might need more than one room, where in the first one it's very easy to check if one room works. So in this one, you might need more than one room, and we need to figure out how do we actually do that. So to start off, let's just look at these examples. So here we have 0, 30, 5, 10, 15, 20. I believe this is the same exact example in the first problem. So here we need two rooms because 0, 30 and 5, 10 occurs at the same time, right? And 15, 20 as well. So you need two rooms, one room for this meeting, and then the other room can handle both of these. And the second one, these are not at the same time, so we can just have one. So how do we change our approach from the first problem, right? Let's just say we have a bunch of rooms and let's say we sort them. So let's say we have 0, 30, 5, 10, 15, 20, 25, 40 maybe, or 25, 60. And then we have 35, 45 or something like this, right? It's good enough. So how do we figure out how this happens? And let's just think about logically what you want to do, right? So if you're trying to figure out for a meeting, do I need to make another room? Well, it would be good if you had a data structure that had all the available rooms. And so what you could do is you can have all the available rooms, and maybe instead of all the available rooms, actually, it would be good if you had a data structure of the rooms that you're currently using and when they will be available next, right? So you have a bunch of rooms, and then you know when they're available, and then you could check if you have a meeting, oh, is there a room that's available? If not, I'm going to add another room because I can't use any of the rooms I have. And if one of the rooms is available, then I can use that room, and then I can just update when that'll be available next, right? So let's kind of write that down. So ideally, we want to have a data structure that has all the rooms we're using and when they will be available next. Then, for a meeting, we can check, is a room available out of these? If yes, let's update when it will be available next. And if not, let's add another room, right? So this kind of thing makes sense. Essentially, this is what we're going to try to do, is we're just going to say, for every meeting, we're just going to check, is there a room that's available? And if there is, let's use it. And if not, we'll update. And at every single iteration, we can just keep track. So at every iteration, or not even at every iteration, we can always just do that. We can do that at the end as well, right? We can just check that at the end. At the end, check how many rooms we have in our data structure, right? So we're going to keep adding rooms if a room isn't available, and then at the very end we can just check how many rooms did we use total. So we're never going to remove a room. So we're only going to add a room if we need it, because if you think about it, the max rooms available is going to be the max rooms at the worst possible time, right? So if we need to use 3 rooms at some point, we can just keep those 3 rooms. We get nothing by removing it later on. If we have to use 3 rooms at some point, we're just going to keep them all. So that's kind of what we're going to do. We're going to have a data structure that has all the rooms we're using and when they'll be available next. So we want to think about what data structure do we want to use? Well, what's our ideal scenario? So if we have all these rooms, ideally we want to know what room, or sorry, not what room, but if we have a meeting, we need to figure out is a room available, right? Yes or no. And how do we, what's the best room to check for availability? Well, if we actually sort these rooms, in terms of time of availability. Right? So we can sort these rooms that we have in terms of availability from, earliest available to last available. But we don't quite need to sort because we only need to check, like for a meeting, we only need one room. We don't need like 5 rooms. So we don't need to sort these. We don't need like a complete sort. We just need to know like what's the earliest available room possible. And if the earliest available room possible is after when we need it, then everything else is going to be worse. So we don't need like a full sort. We just need the earliest available room. So when you don't need a full sort and you just need the earliest available thing, you don't need a full sort. You just need like one element, like what's the smallest element in the list, and you need to keep updating this. You're going to want to use a heap, right? Because a heap is very efficient at getting like the smallest or the biggest element, but it's not completely sorted, so it's going to be faster. So essentially what we're going to do is we are just going to say like, okay, do we have a room available in our heap? And we can just check like what's the earliest available one. If there is one, then we can update that end time to be whatever our meeting end time is. And if there's not, let's just add another room to the heap and let's show the end time. So let's kind of show how this will work in this example. So let's actually copy this down here and let's kind of walk through our logic. So we're going to have a heap and we're just going to initialize our heap to, so obviously we know like for the first meeting, we're going to need one room at least, right? Because for the first meeting, it's going to take a room. We don't have any rooms. So we're going to initialize our heap with the end time of the first meeting. So we're going to initialize, so our first meeting here is 30, right? It's from 0 to 30. So we're going to say, okay, we have a room. It's available at 30. Then we're going to go to the next room and we're going to check, okay, for this start time, is there a room here? Well, we're going to have a min heap. So the min availability here is 30, but we have a room that starts at 5. Well, obviously we don't have a room available here, so we need to add the end time of this room now, right? So we're going to say, okay, let's add another room, and this room will be available after 10. So we're going to add 10 into the heap, and now our heap will be, and like I said, heap is semi-sorted. It's not completely sorted, but we know the first element will be the smallest, so we'll have 10 and 30. Now for 15 and 20, we're going to say, okay, well, is there a room available? So the earliest a room available is at 10, and our meeting starts at 15. So we can reuse this room for this meeting. So if we can reuse a room, we're just going to pop, and we're going to add the new end time, which is 20. And once again, the heap is semi-sorted, so 20 will technically be at the front, and then the rest of it will be like this. Okay, now for this room, we're going to say, okay, well, we have a meeting at 25. Is there a room available? Yes, there is. There's a room at 20, so we're going to pop 20. So we can get rid of all of this. We're going to pop 20. And when does this meeting end? It ends at 60, so this room will be available at 60. Okay, now for this meeting, is there a room available? Yes, there is. There's a room available at 30, so we can pop 30 and then put in this 45. So this will be our heap now. And then finally, you can see we have a heap length of 2. So we are either replacing a time, right? We're reusing a room, or we're adding a new room. So simply at the very end, we can just return the size of our heap once we're done with the whole loop. And that's pretty much it for this function. Essentially, you just use a min heap to keep track of your room availability times. And then every time you have a new meeting, you just check, like, is there room available? If yes, let's replace the time. If no, let's add another room, and let's return the size at the end. Okay, so we can code that up now. And I will say so in LeetCode, you can't like npm install, right? So there is a heap, and there's like a bunch of data structures in TypeScript that are available. There's like a heap, priority queue, min heap, max heap, bunch of stuff. But what I found where actually works in TypeScript is a min priority queue and a max priority queue. So I'll kind of show you like what functions those have and a little bit of a difference in how you have to code it in VSCode. Okay. So here, first we were going to want to sort the intervals. So obviously we're going to interval sort, and we want to give a custom function here. So we will give AB, and we want to just say A0 minus B0, right? We want to sort by start index. Okay. Now we want to make our priority queue, which is, priority queue is basically a heap for all. So for the purposes of what we're doing, priority queue is going to be all the same functions as a heap. So we're going to make a priority queue, new min priority queue. And this is the only one I found that works. Otherwise, you have to actually build one. And this would be like way harder for this problem because to implement a heap with enqueue, dequeue, and like bubble up and bubble down and all that stuff is at least a LeetCode medium. So I'm not going to do that in this problem. Okay, so what we need to do is we need to do something the equivalent of a Python heap push, right? And so what you can do there is there's an enqueue method, and then you can pass it something. So we want to give it the end time of the first interval. So you could do this, and then essentially our heap will have this. But notice there will be one more thing. So actually, this is like a little outdated. So if you actually want to check the topmost element, if you do pq front, if you console log this, this is going to be a little bit unexpected. So if we console log, this is how you get the topmost element in this priority queue. That at least, there might be a better way. Someone can let me know if there is, but let's just look at our actual console log. So return a value. Let's just return 1 for now and just show you like what the console log is going to look like. Okay, so you can see this front has a priority and an element. So it's an object, it's not a number. So when we want to get the value, we're actually going to have to do pq front dot element. So just to show that for the future, that's what we're going to have to do. Okay, so we're going to get rid of this now. But in the actual updated, like I downloaded this priority queue in VSCode, and I'll show you that in a bit. And it actually works a little bit different. So for the purpose of LeetCode, you have an element and a priority, but in the purpose of like the updated structure, it's a little bit different. But anyway, so we're going to have rooms. We actually don't need to keep track of the rooms. We're just going to return that at the end, right? So we don't need that at all. So we're going to say for let I equals 1, I is less than intervals.length, I++. And so what we want to do is we want to like figure out when the meeting actually ends. So we're going to say like const earliest meeting time end equals pq.front dot element, because remember it's an object in this, it's not a number. So what we want to do now is we also want to get the start and end of the current interval. So we can say const start end equals intervals I. Okay. And then what we want to say is if the start time is greater than or equal to the earliest meeting end time, meaning is this available, right? So let's say the smallest time in our heap is like 15, and our start time is 15 or less, or 15 or more, then we're fine reusing the room. But if it's less, then we would have to add it into the queue, right? So if start is greater than or equal to earliest, we can copy this. Then what we're going to want to do is we're going to want to dequeue, right? So dequeue is like a heap pop. So we're going to dequeue, and then we are going to, no matter what, we're going to enqueue our new thing. But essentially what's going to happen here is if we can reuse a room, then we will do a dequeue and an enqueue, which will keep the heap the same length. So regardless of if we dequeued or not, we're going to enqueue, and then you just give it the number here. I put this in the wrong spot. Yeah, so this needs to go here. And like I said, at the very end, we don't really need to keep track of our result. We can just return it. So we can return. And then to get the length of the priority queues, you do pq.size. And I will link the actual like GitHub with these methods. But like I said, they're a little outdated in the LeetCode. So this is how it works here. And we can check if that worked. It did. But yeah, it was kind of annoying because like you can't npm install, where in Python, I think it already comes with like heap. But if you try to do heap, I think it doesn't work. At least for me, it didn't work. So someone can let me know if it does. But essentially, this is how you would do it. And this does work, and it's reasonably efficient. So let's go through the time and the space. So for our sort, that's going to be m log n. And then for every single interval, worst case scenario, we're going to be popping and pushing, right? So you want to be familiar with like how, like, what's the complexity of this. So for a pop and a push is log n. So you could do that n times, which will be n log n. Technically, if you did have, if you actually did pop and push n times, it wouldn't be n log n because you would only have one item, so it would be like n. But let's say, you filled it up like with half of the rooms or the intervals, right? So your queue would be like n over 2, and then you did heap pops and heap push for the rest of it or something, that would be n log n. But either way, this is going to be n log n because the sort, and this is the n log n. And for the space, we did have a heap. So because we did have a heap, like we are going to contain these elements. So that's going to be open space. And yeah, I think there might be other ways to do it other than a heap, but a heap is kind of like the most straightforward way and almost like the intended way to do this problem. And we haven't really done a heap, so I just wanted to show you, if you were curious on how to use a heap on LeetCode, this is how you do it. So you can use a min priority queue and a max priority queue. Works the same way, and all you really need is the NQ and the DQ and size. And I think there is like a heap phi or some kind of, I will link the GitHub in the description for this problem. And so we can quickly pull up the VS Code, and actually here is the VS Code that I was testing earlier. So essentially what you have to do is you have to import min priority queue from this data structures thing. And then this is all the same thing, except it's a little bit different like I think this one's more updated than LeetCode. So if you actually do pq.front without that element thing, it will give you the number directly. So if we console log pq.front, you see it's not an object anymore, it's an element, where in LeetCode it's an object. You do have to say it's a number because it doesn't know like the type, because I didn't specify type. I think you can also give it a type here, and then it will know. So I think you can do something like this, and then you don't need this part. Yeah, so this does work, but when I tried this in LeetCode, so it wasn't happy. So I think these are just like, this is like an updated min priority queue compared to the LeetCode one. Also, if you were to like write this in VS Code, you can use a normal heap, or there's a bunch. There's a min, there's a max, there's a bunch of stuff. There's also a min heap and max heap and all kinds of stuff. But yeah, I'll link to GitHub, and that's going to be all for this problem. So if you did like it, please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.